Let's try a proof together dealing with some congruent triangles. Now we're going to go ahead and write a 2-column proof, but let's first just make sure we understand what the diagram is telling us and what the given information is saying as well. Alright, so first we're told that triangle ABC is an isosceles triangle. So we know that this big triangle of ABC is an isosceles triangle. From this, we want to know some properties of isosceles triangles, which is that these two segments over here are going to be congruent to each other, so AB and BC are going to be congruent, as well as angles CAB and CBA are going to be congruent because those are base angles. So just make sure if you know that a triangle is isosceles that you know those two properties as well. Next, we're told that segment AC is congruent to segment BC, which I sort of just mentioned a moment ago, but we just needed to clarify which side lengths were going to be the congruent ones. So here's that AC segment, and here's that BC segment. Verifying that these are the two segments that are congruent to each other for this isosceles triangle, then the base angles are going to be CAB and CBA, so these two angles are the base angles that are also congruent to each other. The last piece of information that we're given is that angle CAE, which is this angle right here, is congruent to angle CBD, which is this angle right here. We're told that these two angles are congruent to each other, so let's go ahead and just mark those. Alright, now that we've gone over all the given information, let's see if we can use this information as well as other things we know about geometry to go ahead and prove that segment DA is congruent to segment EB. So we're trying to prove that this segment right here is congruent to this segment right here. Alright, so for statement 1, I'm just going to go ahead and put all that given information. And what I think I want to do here is I think I'm going to want to try to prove that this triangle ACE is congruent to this triangle of BCD. Now I think it's helpful to look at these two triangles on the side, so feel free to pause the video and sketch them out yourself so you can kind of see what I'm looking at. We already know that this segment AC is congruent to this segment of BC, and we also already knew that angle CAE is congruent to angle CBD. Because we already know one of the corresponding angles and sides are congruent to each other, maybe we could prove these two triangles are congruent. Well, if we look at angle C up here, that's definitely congruent to itself using the reflexive property, right? So then angle C up here is going to be congruent to angle C. So at this point, we can see that we have an angle, which is down here. We have a side, which is going to be this side right over here. And then we also are going to have another angle, which is up here. So we could prove these two triangles are congruent using ASA. So for statement number 2, I just want to go ahead and say that angle C is congruent to angle C. And we can say this by the reflexive property of congruence. So we were given a corresponding angle, and then we were also given a corresponding side. We just had to go ahead and use the reflexive property of congruence to say that we had another corresponding angle. We can use this information together to say that triangle ACE is congruent to triangle BCD. We can justify this using the ASA theorem. Now that we've confirmed that these two triangles are congruent to each other, we can say that all their corresponding parts are also going to be congruent using CPCTC. Now the particular part of these triangles that we're going to care more about are going to be the side lengths of DC as well as EC. Now keep in mind that is going to be true because we're trying to prove that segment DA is congruent to segment EB. So those are these segments here of DA or AD and this BE over here. So we're going to try to focus in on the segments that have to deal with that side or the pieces that are going to be connected to that segment. And so let's go ahead and just say that segment DC is congruent to segment EC. At this point, we know that segment DC and EC are congruent to each other, and we're trying to prove how the segment of AD or DA is congruent to the segment of BE or EB. And so I think we're going to have to do some segment addition. Because of that, let's go ahead and see if we can convert some of our congruence into equality. So remember earlier that we knew that these two segments of AC and BC were congruent, and we also identified that the segment DC and EC are also congruent. So from that, let's just turn each of those congruences into equalities. And we can say that by definition of congruent. So if the segments are congruent to each other, then they have equal length. A little bit ago, I mentioned the segment addition postulate. So maybe we could say something how like segment DC added to segment AD would equal this entire segment of AC. And we could also say something like segment CE plus the segment of EB would then equal this entire segment of CB. So maybe we can set up some equations that look like that. So here's one of our equations, where we know AC is equal to DC plus DA. And here's our second equation, where we know BC is equal to EC plus EB. And remember, we can justify this by the segment addition postulate. At this point, remember that this segment AC and BC are equal to each other because we knew that their segments were congruent to each other. So if that's true and these two segments are equal to each other, then the sum of their parts should be equal to each other as well. We can say the sum of DC and DA is equal to the sum of EC and EB. This would be by the substitution property of equality. Now, if we know the sum of these two segments is equal to the sum of these two segments, but we also know that DC and EC are equal to each other and have the same measure, then I think we should be able to subtract the length of these two segments from both sides of this equation so that we are just left with the fact that DA's measurement would be equal to EB's measurement. And so if we subtract the same value from both sides, we're going to get that DA is equal to EB. And this would be by the subtraction property of equality. And then for our final statement, if we know that the length of DA is equal to the length of EB, so we can say that segment DA is congruent to segment EB. And that's going to be by definition of congruence, because if we know that two segments have equal lengths, then they must be congruent to each other. Alright, so that wraps up this proof. If you found like this video helped simplify down the process of how to write this proof, feel free to let me know in the comment section down below and give the video a thumbs up as well. If you think that a classmate or friend might also find it helpful, feel free to share it with them. And as always, keep up the great work that you're already doing, and I'll see you in the next one.